Okay, Luke, so we're back in Sydney.
We are indeed.
Here we are. So it's time to get into some of the recent thing that's been in the press. I don't know if you saw, there was a story over the last couple of weeks now about this discovery of water on a planet in the habitable zone around another star.
Ooh.
And the media ran with this, and there was even a story that I saw where an astronomer said there was 100% chance that there was life on this
Did
planet.
they?
Yeah.
Wow.
That's quite a bet. It's quite a bet.
Interesting.
So I thought we should discuss this notion of habitable zones. Where should we expect to find life in the universe? And we hear a lot about habitable zones around stars, but they're a bigger concept, right?
Yeah.
So let's just start with stars. So if somebody said to you that there's a planet in the habitable zone, what sort of picture springs to mind?
So the nice thing that you can do with just sort of the back of an envelope and for a bit of fun is just say, all right, I've got a certain star of a certain size. How far away from the star does a planet need to be in order for, if there was any water on its surface, that water would be liquid rather than, oh, I'm too far away, it's all frozen, I'm too close, it's all vapor. Where's that? And there's a sort of rough calculation you can do with that. It has to do with how much energy you receive from the sun and then how much you radiate out at a certain temperature. And then if that temperature is roughly, between 0 and 100, then you're sort of in the right ballpark. And so that's the classic habitable zone. Where can I put my planet in order for there to be liquid water on the surface? Now, there's an assumption there already, right? I'll have some water, and then, hey presto, I'll have some life.
Well, that's right. But it's an interesting thing, right? The phrase is habitable zone, but that doesn't necessarily mean that a planet in the habitable zone is habitable.
Right, yeah.
So Mars is on the outer edge of the sun's habitable zone.
Yeah.
And if we went there, we would be dead pretty quickly.
Very quickly, yeah.
That's right. And Venus is on the inner side of the habitable zone. And again, if we were transported there, things wouldn't be so good. All right. So I think the phrase habitable zone conjures up this image of a planet like the Earth.
Yeah.
But I see that there's been a bit of backlash, I guess, with regards to the media reporting of this planet, because it's sometimes reported as a super Earth.
Yeah.
Or a small Neptune. Okay. And it might actually be a gaseous planet rather than a planet with a solid surface.
Yeah.
And so the notion that there is liquid water in the form of oceans and ponds and pools, rather than just some sort of water vapor in the atmosphere, I think has misled a few people.
Yeah.
But this notion of habitable zone, of course, is an important one to think about where life could potentially be. We don't expect life to be in the sort of frigid outer parts of systems around stars, and we don't expect it to be on planets orbiting too close to stars. Yeah. And of course, what we also know is that the habitable zone around different stars depends upon what kind of star it is. So if you've got a big bright star, right, so it's very hot, then its habitable zone is further away. Yeah. And if you've got a cool star, like an M-dwarf star, then the habitable zone is quite close into the star. So, and these are things that change with time, right? Because a star's brightness changes. Yeah. The sun is getting brighter very slowly. It's not the cause of global warming. So the sun is steadily getting brighter, so its habitable zone is actually very slowly moving outwards. Yeah. But there's a more general concept of habitable zone that you don't hear about so much, and that's this notion of a galactic habitable zone.
Right. Well, I should say before that, one of the reasons why we focus on water is the first thing, and then this will sort of more generally why we're focused on that is we think for life to exist, we need chemicals to sort of come into contact with each other and bond with each other. And the thought is, if everything's frozen, nothing's going to move, and so you won't get that sort of things mixing around and hopefully making interesting stuff. And if that's too far out. If you're too close, then everything's in a gaseous state, and things will come together and then be blasted apart again. So we think that that's why we need some liquid, but we need a bit more than that, as you say. So one of the things we'd like, in our sort of neighborhood is obviously, if you've got a star, you would like it to have a planet in the first place. And it seems like you're more likely to get a planet if you're in a part of the galaxy where there's been lots of time for stars to build up those heavier elements. So this is what astronomers call the metallicity, in a way that no other physicist or scientist would call something a metallicity. What we mean is just all the elements heavier than helium, roughly. But all the things that are made in stars, and so once you get the output of stars, you'll get carbon, and that's probably one of the important ones, oxygen, and all that sort of stuff. So one of the first things is it seems like you're more likely to get a planet, and so more likely to get a planet in the habitable zone if you're in a bit of the galaxy, right, where there's lots of these heavier elements. So there's probably not going to be life way out because it's just sort of pristine gas and stars.
Okay. Oh, so I was going to say, this is not uniform then, right?
No.
When you look at a galaxy and you see the spiral arms, it all looks reasonably uniformish.
Sort of.
Right, but you're saying that the outer edges are not the same as the inner regions.
Yeah, probably they're lagging behind. So you also, there's more stars closer to the center. Now, that's a good thing because you've got more opportunities there. But you're also now... you would like your one, like we've got the sun here and it's just that far away and it's just nice, we're in its habitable zone. We would like, at that point, once a planet's got its own star, everyone else can just stay away, all right? Just all the other stars can go away. But if you're into the center, near the centers of galaxies, you've got a couple of problems. You've got the possibility that other stars will come wandering through your system. So if another star came wandering through the solar system, that would be a very bad thing. There's a very nice paper by Fred Adams and some of his collaborators about, it basically took all these simulations of here's the sun, here's the Earth, let's just throw a star at a certain distance away and see how close we've got to throw it at a certain velocity in order to make the orbit of the Earth go from being round to being something a bit too oval shaped for life. So you've got stellar encounters, they're a problem. Mm-hmm. You've also got the fact that stars blow up in various ways. If you're in a place where there's young stars, you'll get young hot stars. So big stars burn out very quickly and blow up. Anything bigger than about 8 times the mass of the sun. So that's called a core collapse supernova. You've also got old stars, stellar remnants. They're in this sort of... as long as they're small, they're stable. You have something called a white dwarf, which is held up by what's called quantum degeneracy pressure. But if one of its neighbors sort of drops some mass onto it, its own gravity starts building up, it can go past the limit of, I'm not stable anymore, and it will blow up. And that's called a type 1a supernova. And those will happen sort of a billion-ish years after the star formed in the first place. So you don't have to be at the middle of the action. You could just have one of those wander past. You've also got to worry about gamma ray bursts, whatever they are. So we see these very bright sources of gamma rays coming at us, and we think that this is a very special type of explosion. So for very, very large stars, there's a lot of ideas about how this might actually happen, but the thought is for sort of maybe 30 to 40 solar masses, when they do a core collapse, they really do something special and a whole lot of gamma rays comes out. And those will be especially dangerous. But one of the things we notice from observations is these seem to happen more often, or are more likely to happen, where the metallicity is lower. And so actually... there's a paper which follows the line here of actually, okay, so here's my galaxy, and I'm out here, and all the gas around me is fairly high metallicity because that's where I am, and that's good. So there probably won't be a gamma ray burst here. But if another like dwarf galaxy comes in, a nice pristine one, and just sort of starts wandering around, there's a possibility that its nice pristine gas will make a star which then does a gamma ray burst, and that's going to hit me because they have such a large blast radius.
Okay. And
so there's all of this sort of stuff comes in as we start to think about where we want to go in the galaxy.
So if I've got this picture right, our Milky Way, nice flat spiral galaxy, in a region, too many stars, too dense, lots of activity going on. So that's where, a place which we wouldn't really expect there to be life.
Yeah, quite possibly not life.
Yeah.
Friendly.
Yeah. Outer region, less metallicity, less stuff for making planets, etc.
Yep.
So there's this band sort of midway out where we find the sun, of course, which is like the habitable zone of the galaxy. Mm-hmm. But this habitable zone is not a fixed thing, right? Because the metallicity of a galaxy changes over time.
Yeah.
All the stars way back when started off as having no metals, and the metallicity has been steadily increasing. So the habitable zone is sort of increasing in size, but you've got these gamma ray bursts that could be popping off as well, which are sort of truncating the habitable zone. So habitability in a galaxy is a kind of complicated interplay of lots of different things.
See, there's another one I read a paper on recently, I think it was this year actually, which was when we look out into the gas in between the stars, we see there's sort of hot diffuse gas and slightly warmer, warm, sort of colder neutral gas. And there's what we call molecular clouds, giant molecular clouds. So these have the mass of about 1 million times the mass of the sun, but they're relatively compact. And what we think is that those will eventually become the nurseries of new stars. And there's actually, going back to a paper from Fred Hoyle in 1939, a question about what happened if the solar system wandered through one of these giant molecular clouds. And during that passage, it's possible that the sun itself would accrete matter from the cloud as much as the mass of the Earth would accrete onto the. So that's kind of interesting. In particular, you might get one of the speculations is, and it's hard to know without a specific model, but you might get a whole lot of matter collecting into the outer atmospheres of the planets. So that would seed a lot more cloud formation, and so you might get a runaway sort of snowball Earth. You get more clouds, you get more rain, it gets colder, the rain turns to ice, and then all the light gets reflected, and so your planet just sort of snowballs for a little bit. And it seems like there'll be some sort of encounter. That will depend again. If you're too close to the center, there's probably more giant molecular clouds there. You're a bit safer if you're further out. You're a bit safer if you just keep nicely in line rather than trying to sort of weave your way around through the solar. Actually, no, sorry, the opposite. If you stay in line, you want to. If your orbit of the galaxy, rather than just going straight around, if it sort of does this as it goes around, you'll spend less time in the disk where the spiral arms are and where we assume most of the giant molecular clouds are. And so there's actually a bit of safety in sort of weaving your way through the disk. So even then, it's not so much a zone. You could be in the same zone as someone else, but if you're bouncing your way around, you'll be a bit safer. So,
and there's another issue, which again, just because the star is in the habitable zone doesn't mean it can be habitable. Most stars, as we know, are in multiple systems, binaries, triples. And anybody who has recently read the three body problem book, which is very interesting. I won't give away the the main plot, but part of it is that life on a planet in a system of multiple stars is not easy.
Okay.
So can we take that concept bigger?
Yeah,
right?
Sure.
We've spoken about habitable zone in a galaxy. Is there a universal habitable zone? Because we know our Milky Way is in the local group with Andromeda. Most galaxies are in groups, but there are big agglomerations of galaxies known as clusters where there could be hundreds or thousands of galaxies, and often within these galaxy clusters you will find potentially a big galaxy in the center, potentially an active galaxy. So can we imagine what the habitable zone of a cluster of galaxies look like?
Well, you've put your finger on one of the main things we have to worry about is if there is an active galaxy, what's called an active galactic nucleus or a quasar. And there's a very entertaining / horrifying paper by, I think Avi Loeb's one of the authors, I'll put it down below. Just saying, all right, suppose, so a quasar is we see these extraordinary bright things in the very distant universe. And we think the best idea about how they're being powered is that matter is falling onto a black hole, and in its last sort of flight as it falls in, it gets very hot and starts shooting copious amounts of energy and radiation and such into the universe. And one of these, if you get a very big one, so the one at the center of our galaxy, there's a black hole there, it's about 1 million times the mass of the sun, and so if it got suddenly fed by a whole lot of material, it might fire up into an active galactic nucleus, but for the moment it's just sort of chilling out. But if you get a very active one that's on the upper end of how big these can be, say 1 billion solar masses, it could, according to this paper, it could strip the atmosphere off a planet at enormous distances, at thousands of light years away. It not quite where we are. We're about, in astronomy units, we are from the center of our galaxy 8.5 kiloparsecs is the unit. But at about, not quite 8, but about maybe 1.5, if you have one of these things fire out, which is an enormous distance in in these scales. But if you're in that distance, if one of these fires up, then there's enough energy there to take off take an atmosphere off a planet. And so that's part of the larger environment. If you're in a cluster environment, there might be more of these things around.
And of course, in a cluster environment, there are more galaxy collisions.
Yes.
You have actually got background gas as well in the cluster, and that can radiate X-rays and all that kind of stuff. I don't know if anybody's actually calculated what the habitable zone of a cluster would look like.
No, I don't think so.
So maybe we should think of writing a paper.
Yeah. Actually, there's one I've don't tell anyone. The one I've always wanted to do is, the habitable zone during a collision.
Yes.
So I think we've totally got to get onto that.
Absolutely.